Hello, this is Miss Salter, and I am doing a video here on a couple of the problems from the adaptive practice on the ck12 orbital motion assignment. One is about the satellite that is orbiting around Mercury. The other one is the geosynchronous satellite around Earth. And the basic picture that has to do with both of these is on the helpful information document on Google Classroom, and I'm going to draw it here just to show you what all the little pieces mean. So we start off with a drawing and a satellite and a planet. So we have a planet and we have a satellite and we have two equations that we're mainly working with here in this section. We're working with our force of centripetal force, Fc, equals mv squared over r. This is about the satellite. The satellite is rotating around the center of the Earth just like an object on a string or a bucket on a string. So we have a centripetal force, and we have a mass, which is our satellite. And we have a satellite that is moving at a velocity. It has an acceleration toward the center. That acceleration is equal to v squared over r, which is why it's mv squared over r, because the v squared over r equals a and f equals ma. And then we have a distance r, which is the radius between the center of the rotation and the center of the orbit and the center of the satellite or the object. The other one we just got, the other equation we got introduced to is the force of gravity, which is equal to the gravitational constant times m1 times m2 over r squared. In ck12, they call the r squared d for distance. It's the same thing, because if you notice here, we have a planet, we have two bodies. The planet we're going to call m2, the satellite we're going to call m1, and they are separated by a distance apart, which is r, radius of the rotation. And that is squared, and then we have that gravitational constant. Because of the way these two set up, we can set these two equations equal to each other because Fc equals Fg. Fc is the force, centripetal force of the satellite. Fg is of the system. So it's basically measuring the same thing. So what we're going to do here is I'm going to move this up. We're going to see how these two equations get set opposite each other. So we have Fc is equal, we have it m v squared over r. We have g m1 m2 over r squared. Well, r squared, it would be the same as saying r times r. M from the left side is the same mass as m1 on the right side, so they cancel out. And one of the r's on either side cancels out. So that leaves us with v squared equals gm2 over r. And m2 is the mass of the planet. So we can change that to v equals the square root of g, mass of the planet, over r. And that will get us the first part of both of our problems up above. The speed of the satellite. Then we can put onto this then the other one we have from uniform circular motion, which is our equation v equals 2 pi r over t, the period. We're going to insert that into our equation for centripetal force. So instead of that equation, Fc being equal to mass velocity squared over r. So we're going to start with mv squared over r equals g m1 m2 over r times r, or r squared. This whole section here, we are dropping into in place of that v. Yeah, so then we get a mess. But it's okay, because we're going to take some of these out. So we're going to take these m's out. We're going to take an r out. So then we are going to be left with 2 pi r over t, which means the same as v, squared, equals g m2 over r. Okay, cool beans. So now what we're going to do is we are going to take this and we're going to square this stuff on the left side. So that looks a little better. 4 pi squared. And we're going to use pi equals 3.1415. On ck12, you got it better. They kind of rounded everything, so you could use just 3.14. But I use 3.1415 because I like going to 4 decimal places inside my equations. R is squared and t is squared equals g m. Nope, not up there. I had that trouble before. I kept mistaking it for squared, and it's not. It's m2 over r. Okay, so now I can take this r off of here because it cancels out with one of these r's. So that becomes just an r up top. And then I times it by t squared and divide it by gm2. So I end up with t squared equals 4 pi r pi squared r squared. Stop it. Oh, that's awful. Pi squared r over gm2. And then, of course, that is equal to t equals the square root of 4 pi squared r over gm2. Uh-oh. Now somehow I did that wrong. Oh, that's because, oh, look at that. Okay. This part here is, this would be times 1 over r over 1. So that would be times by r over 1. So instead of this becoming r, this is actually, and this is why you got to be so careful when you are doing this, is that is actually, let's erase that part too. Well, that's really ugly. This is actually 1, that's actually a 3, that is a 2, and a 3, and that is a to the 3rd. Oh, and that's why sometimes this is so much better when you write this all out and you're trying to figure it out, because you can see where everything's going. Okay, that is our second equation for the equation for the second part of our problems. All right. So now we just have the problems to deal with. So let me pause the video and I'll get that set up for you and then show you how those problems are set up. Okay, so I've set up these two problems down at the bottom of our document here. I brought in the value of g, which is 6.67 times 10 to the negative 11th, and a whole bunch of awful labels after that. And the mass of the Earth is 5.98 times 10 to the 24th kilograms. So our two equations are here: velocity of or speed of the satellite and the period of the satellite. So for the first problem with Mercury, v is going to equal the square root of g 6.67 times 10 to the negative 11th times the mass of Mercury, which is 3.2 times 10 to the 23rd, all over the speed. Now, r. Okay, here's the deal here. R here is going to be the radius of the planet, 2.43 times 10 to the 6th meters, and the orbit, which is from the surface of the planet to where the satellite is, 265,000 meters. So you have to add those two numbers together, and when you do all that math, your velocity comes out to be equals 2,811 meters per second, and then you round it to get the answer that was on the adaptive practice. If you're doing this for the other one, you're going to use the same thing. V equals gm2 over r. Over here, you've got g 6.67 times 10 to the negative 11th times the mass of the Earth, 5.98 times 10 to the 24th, all over our radius, which is 4.23 times 10 to the 7th. Okay, as you can see on the screen here, I wrote in the t for both of our problems. We put in 4 times pi squared, and then, we need to, don't forget to cube the r values. And then over top of the bottom, you can see the answers there rounded. Thank you.